Hi everyone, I'm Anahit and I'm from a company called Solita, and welcome to my kitchen, which is in Finland. And I'm going to be talking about serverless data streaming today. So first there's going to be a short introduction, then we'll look at the AWS services that we have used in some details, and then finally I will wrap up with some gotchas and the lessons learned from the process. So first, while you're looking at my cat illustrating some 4 stages of software development for you, I'll tell briefly about myself. So I'm from a company called Solita. I'm a lead cloud software engineer there. And I'm also a member of the AWS Community Builder program, which is a program for AWS enthusiasts and active community members. And for the past 3 years, I've been working as part of the data and AI team at the Finland's National Public Broadcasting Company, YLP. And you can basically think of YLA as a sort of the BBC in Finland. It provides broadcasting, radio, streaming services to the entire Finnish population. And it's funded from taxpayers' money. There's no advertisements anywhere. And it's also highly respected over here, having some bold missions of strengthening Finnish culture and society and preserving, expanding the quality content in each language. So, as I said, YLE has a streaming service. It's called YLE Arena, and it's not just a streaming service, it's actually the biggest streaming service in Finland. And not only that, it's the only streaming service in the world that beats Netflix in its region. So, YLE Arena has bigger audience than Netflix in Finland. No other service in the world can say that. And our team in particular is responsible for Arena recommendations engine. And also we do a thing called image personalization, where we don't only try to personalize the content that we're going to get, but we also personalize the way we represent the content. So we'll have several cover images, for example, for the same video. And then based on what we know about you and what we think will be more appealing to you, we will show you one of those images. And I'll be talking about it more in details shortly. So as a data team, we are dealing with data. And when I speak about data, it's mostly user interaction data, which is nothing else than just some JSON with the information about the user interaction that we need to know. And why do we even care about the data? Well, as I said, there's no cash flow from advertisement. We are not selling the data to anybody, not making money out of it. What we actually want to do is to understand the customers, and that way to help provide even better services for everyone. So let's talk some numbers. How much data are we talking about? And it's over 500 million requests per day. Unlike what I said at AMA, it's not 500,000, it's 500 million requests. So 500 million requests per day. And they go up and down during the day, and they reach the peak around prime time in the evening when it's roughly 600,000 requests per minute. And all that requests end up in roughly half a terabyte of data per day, which is stored in both JSON and Apache Parquet formats. And in addition to those daily variations that we get, we might also get some spikes in incoming traffic. For example, if something happens in the world, people go to YLE services to read the news, to check what's happening, and we might have some occasional spikes in incoming requests. But there are also some predictable spikes, like some sports events, for example. And this particular one is the last year's parliamentary election result night, which coincided with Women's Hockey World Championship finals, and Finland was playing. And if you need to know one thing about Finland, is that they love hockey here. So everybody who wasn't watching the election night, they were watching the hockey. And at that night, we got roughly 2.5 million requests per minute, and it was quite a nice stress test for our systems and for my nurse in particular, because I was on call that night. It went well. But enough with the introduction, let's go into some technical details of our systems. So YLE uses AWS as its cloud provider, and this is a very high level overview of our data system architecture that we have over there. And no worries, not going to go into details of every single system here. Instead, I will just concentrate on the part that I promised, which was the serverless data streaming part. But let's first of all think of the high-level goals that we had when building this pipeline. So they can be roughly separated into the goals can be roughly separated into 2 parts. First, we want to load data into a data lake in a columnar format. And secondly, we wanted to enable all sorts of content personalization through near real-time analytics. So things like cover image personalization, for example, that I talked to you about earlier. And why serverless? Well, nobody says it better than Dr. Anahit Pogosova, CTO of Amazon, who is the man of many great quotes, one of them being, no server is easier to manage than no server. So I'm not going to disagree with that one here. So let's take a closer look at our serverless pipeline. So we get all these user interaction requests being sent to our component called Analytics Collector. And if you're familiar with AWS, you might stop me right there and say, hey, there is a Fargate and it's not serverless. And well, I won't really disagree with you too much, but I will say that it's the most serverless way how you can deploy containers in AWS, because you just drop your Docker container, you provide some CPU and memory requirements, some auto-scaling requirements, and then Fargate takes care of the rest for you. So it's pretty close. But I'm not going to go into details of Fargate here. I will just say that our analytics collector gets the incoming request, it filters them, cleans them up, batches them, and sends them forward to a stream. Oops, sorry. And as a stream, we use a service called Kinesis Data Streams. And what it is, it's a fully managed and massively scalable service to stream data on AWS. So after you write the data to the stream, it is available within milliseconds, and it's stored there for up to 24 hours or up to 7 days if you need to replay it later. And to read the data from the stream, you need to write your custom consumers, and there are plenty of options to do that. You can use EMR, ECS, and so forth. We are using Lambda Functions to read from the stream. I'll be talking about it shortly. And finally, how the Kinesis stream is scaling? Well, it uses shard as its unit of parallelism. And what the shard is, you can think of it as just an ordered first in, first out queue. And a stream is a combination of several such queues. So each shard has a limited throughput. It's 1 megabyte per second, 1,000 records per second of incoming data. And if you have more data, you just need to have more shards. So if you recall, I told you that during the evening prime time, we have roughly 600,000 requests per minute. So if we make an assumption that they come uniformly through the minutes, it will make around 10,000 requests per second. So with 1,000 record limit, we will need something like 10 shards to accommodate all that data. Well, the reality is we actually have a bit over 40 shards in our stream. And that is because of this unexpected burst of incoming traffic that I told you about. So we want to be prepared if something unexpected happens and we get more data that we can process. We don't want to lose that valuable data. So we end up over provisioning our stream. And you might also think that why not to just add as many shards as possible and just sleep well. Well, of course, there's a catch. With Kinesis, you pay for the data that you are streaming, but also you are paying for each shard that is put up on your stream. So it's always a balancing between how many shards you want to have open and how many of them you need actually. So there's plenty of ways to write data to Kinesis stream. There's even some direct service integrations, like you don't even need to write a single line of code to do that. We are using the most flexible way and the way that allows you the most control for providing data, and that's AWS SDK, or basically Kinesis API calls. So all the examples from here only will be for Node.js SDK, but all the same considerations pretty much apply to all the other SDKs. It doesn't depend on the language really. So with Kinesis API, there is two ways to write data to the stream. You can either write a single record, or you can write batches of records. And it is always recommended to write batches of records because you save on API calls, you save on network throughput latencies, you don't send back and forth some boilerplate payload. So it's always recommended to use batch operations. And when you're sending a batch of records to a stream, you provide the name of the stream, and then you have the array of records that you want to write to the stream. And each record in the array contains the data, so the payload you write to the stream, and also a string called partition key. And what partition key is the way that Kinesis stream decides which shard to write your data to. So when you write a record to a stream, Kinesis calculates a hash value of the partition key, and each shard in a stream is assigned a range of hash values, and those ranges don't overlap. So your record based on that partition key ends up in one and exactly one shard. And in our case, and actually it's recommended to use as random of a partition key as possible, because you want to spread the data uniformly across all the shards. You don't want to overwhelm a single shard. And we are using the surrogate user ID as a partition key, for A, because it's random enough, and B, because we want to get the requests or the events of the same user in order. So we want to get, for example, a video play start event before we get the video pause event for that user. So we want to order the user's event. So if you recall, I told you that the events in the shard are ordered, so it's an ordered queue. So by sending the events of the same user to the same shard, we managed to get the events in order when we read them. So, okay, we wrote the data to the stream. What happens next? I mentioned before that we are using Lambda function to read from our stream. And Lambda reduces a lot of heavy lifting. It takes care on your behalf of things like tracking where exactly in the stream you are at any given moment, where exactly in the shard you are at every given moment. It does a lot for you, but of course you need to understand how exactly it is working. So by default, one Lambda function is invoked once per second, and it reads batches of records from a single shard. And so there's going to be as many parallel Lambda functions reading from your stream as you have shards, and each Lambda will be reading from its dedicated shard. Unless you're configuring something called Parallelization Factor. So if you need to increase the processing speed of your stream, you can throw up to 10 Lambda functions at every shard of your stream. So you will have up to 10 Lambda functions reading from the same shard, and thus your processing speed will increase. And it will also mean that you will have up to 10 times as many concurrent Lambda executions as you have shards in the stream. And this is an important point because of a thing called Lambda concurrency limit. And you're probably familiar with the fact that there are limits to how many concurrent Lambda executions there can be per account, per region. By default, it's 1,000. So imagine you have a stream with, say, 100 shards, which is not totally common. And then you have a parallelization factor of 10. This will mean you will have 10 times 100 Lambda functions, so 1,000 Lambda functions, reading from your stream at all times. And that will probably be just fine until somebody else somewhere in your organization, in your region, in your account decides to write some very business critical Lambda function that does something extremely important, and that Lambda function starts to fail for unknown reasons. And the reason is that your Kinesis stream with the Lambda consuming it consumed the entire budget of Lambda functions that was allocated to your account. And so it can have a very big blast radius, hitting this limit. So you should keep a very close eye on that. And speaking about things that you need to keep close eye on, so what happens if there are some error situations? So imagine you have a batch record in your batch. So your Lambda calls each shard once per second and gets a batch of records and tries to process them. And then in that record, there was a batch. In that batch, there was a batch record, and the entire batch is returned back to the stream. And Lambda takes care of retrying for you. So it will retry the same batch over and over again until it succeeds or until the data expires. And if you recall, I said that by default, data is stored into the stream for 24 hours. So in this situation, your Lambda will retry and retry and retry for 24 hours. It will fail because of one batch record. And then finally, after 24 hours, your data expires and the entire batch is being dismissed, so they're thrown from the stream. So you're losing the entire batch instead of losing just that one batch record. But actually, bad things don't stop there. They start there because until your Lambda is processing that shard or that bad batch, it stops reading any other records from that shard. So all the other shards in your stream, they go on with their lives. Everything is good, but that one shard is stuck because of that one batch record. And that's why it's called poison pill situation, because that one batch record has pretty much blocked your entire shard. So in 24 hours, when it's finally dropped, you end up with a shard that is probably filled with records that were written around the same time that particular batch. So they expire around the same time. So your Lambda most probably won't even have time to process all that records from that chart that are soon expiring. So they will keep expiring and you will end up losing much more data because of that. So there was just one bad record and you end up losing tons of data because of that. And luckily, nowadays you can customize those things. So nowadays you can tell Lambda how many times maximum it will do the tries. You can also tell it what will be the maximum age of the record you want it to retry. And you can even split or bisect the batches, the bad batch, recursively. So Lambda will split the bad batch into parts and will send the part separately. And it will continue doing it recursively until it hopefully sends all the data except that one bad record. So there's plenty of options for that, which you should be aware of when working with Lambda. So let's return once again to our agenda. So we wanted to load the data to a data lake in a columnar format. And so far, we have got all the requests. We patched them, we send them to a Kinesis stream, and then we have a Lambda function reading from that stream. And the Lambda function is called flow through Lambda. And what it does, it basically routes different events to different destinations. So in our stream, we have inherently different events, by their structure. So for example, if a user reads an article, it's a completely different event from watching a video, for example. So we want to separate those events right at the beginning, and our router Lambda does exactly that. It gets the events, it checks what kind of event it is, and then it sends to different destinations. And here comes the second service in the Kinesis family, which is called Kinesis Firehose. And this one is also a fully managed service, but this is for loading streaming data to a destination, not for streaming the data. And as a destination, there are plenty of options to choose from, but the one that is important for us in this context is S3. So FireHost allows you to stream the data with 0 lines of code to S3 and other destinations. So you pretty much only need to do some configuration settings, and that's it. Another nice part about FireHost is that it scales automatically. So you don't have shards to take care of and to manage. You just rely on FireHost in that sense. And finally, again, without any lines of code, FireHost does things like batching, compression, transformation, and it also can convert data from one format to another before writing it to destination. So in our case, FireHost converts JSON data to columnar Apache Parquet format and writes the data to a destination, pretty much without us having to write any code for that. So that way, we achieved our first goal of loading the data to the data lake in a columnar format. And I'll go briefly through the differences of the services I just described. So Kinesis and FireHost, both of them are fully managed services. Streams are for streaming data, and FireHost are for loading data to a destination. They have different retention time for the data that is written to them. And one key difference is that Kinesis streams scale, you need to scale it manually and it scales into shards, while FireHost scales automatically. And the other key difference is that for Kinesis, you can and should create custom stream processors that will consume the stream. And FireHost can't have any consumers. You can't create custom consumers, but instead, FireHost can batch, compress, and convert data out of the box. And you can also write small transformer Lambda functions that will transform the data before loading it to a destination. So let's get back to our agenda now. So we got the first point. The second point was enabling content personalization through near real-time analytics. Let's look at our architecture now. So that's the second branch of it. And here we can see one more service from Kinesis family, and it's called Kinesis Data Analytics. And what Kinesis Data Analytics does is it's also a fully managed service, and it allows you to run queries on your streaming data. So you can run joins, filters, aggregates over time-based or row-based windows in your real-time streaming data. And it's a very useful service for things like real-time fraud and anomaly detection, some game scoreboards, and things like that. And the way it works is you can attach a data analytics application to either a Kinesis stream or a Kinesis Firehose, and it will send the result of the query to either another Kinesis stream, another Firehose, or it can send the results to a Lambda function, which pretty much means that you can do anything you want with that data after that. And that's exactly how we are using it. We are using Kinesis Data Analytics for our content personalization. So remember the thing I told you about showing different images for different people depending on the things we know about you. So for that purpose, we are using a machine learning model called Contextual Bandit, and it's an online unsupervised learning model. And to learn, it needs to be rewarded. So we show you an image for a video, and you start to watch that video, and we take it as a good sign. So you like the image, probably it was your interest. We want to reward the model for that. So for that purpose, we need to analyze that data that is being streamed and send the aggregate data. We send the aggregate data to a Lambda function that in turn, based on that data, decides which model to reward. And in that way, using Kinesis Data Analytics, we actually achieve our second goal of enabling near real-time analytics. So let's take one more look at this architecture I was talking about. So we get the incoming requests for user interaction data from all around the devices, and it gets to our service called Analytics Collector, which filters the data and batches it and sends it forward to a Kinesis stream. There is a Lambda function reading from Kinesis stream and deciding based on what is read, which firehose it will send the records to, and it sends different events to different firehoses, and firehose in turn takes care of compressing and converting the data to a columnar format and writing it in batches to S3. And on the other hand, we have several Kinesis Analytics applications attached to different firehoses that are aggregating data over a time-based window and send the aggregation results to a Lambda function, which in turn rewards different machine learning models based on the data that Kinesis Analytics provided. So that's basically about it. So to wrap it up, what were some of the gotcha moments here and lessons to learn? And of course, there were plenty, but time is limited, so let's just stick to a few of them. So the first one is about Kinesis limits. So Kinesis limits are per second. So it's 1 megabyte per second, 1,000 records per second. And the problem here is that CloudWatch metrics are actually per minute at best. So you will get an aggregate metric over a minute, but you will never see a second-to-second situation per stream. And why is this a problem? Well, imagine you have a shard and you have 2,000 records per minute of incoming throughput, which is not a lot for one shard to handle. So the question is, can you still exceed the throughput? And the answer is unfortunately yes, because you can get all that 2,000 records during the first second of that minute, and while the limit for the second is 1,000, you will just get 1,000 and the rest will be lost. So the bottom line here is that you shouldn't blindly trust the metric that tells you that everything is fine and you have enough throughput in your stream. You usually need to look deeper than that. And speaking about limits, remember FireHost is a wonderful service that scales endlessly on your behalf. The question is, does it really? So you read the documentation and it says it is a fully managed service that automatically scales the large throughput of your data. And so far so good. But then you keep on reading, as you always should with the documentation, and you see this part, which says when direct food is configured, each Kinesis Data Firehose delivery stream is subject to following limits. And then it will go on and tell you that the limits are soft limits and hard limits, you can increase them and so on and so forth. But the key here is that there are limits and you need to know about them, not just assume that things will work out of the box. And at least now there is a metric which will actually tell you if you reach those limits and exceed those limits. The next one is very important. We actually touched on that in the AMA section. It's related to timeout. So all API calls timeout, and there can be network glitches or other reasons for that. But timeouts will happen, and luckily SDK does retries with timeouts on your behalf. But the problem here is that the default timeout values are way too high. So the default timeout for Kinesis is 2 minutes. And imagine you have a Lambda that is waiting for 2 minutes for a connection that probably will never happen. So you should never use default timeouts. Instead, you should always configure the timeout for your service on your own. And this is an important part because this is related to all the AWS API calls. It's not Kinesis specific. The same applies to Dynamo, the same applies to SQS and whatnot. So it's a very important point here. And last but not least, probably my favorite one is the batch operations. So remember this put records call, which is used to write a batch of records to a Kinesis stream. So you have a piece of code that just logs an error if you get one. Probably if you don't see any error in your logs, you assume that things are fine and everything is working perfectly. Well, you probably guessed it right. They are not. And the problem here is that batch operations in AWS, they are not atomic. They are not either or succeeds or all fails. There can be situations where you get a success code and part of your batch has failed. For example, because of throttling. There can be situations where the entire batch has failed. You still got the 200 success code. Actually, you pretty much never, or you get an error code very, very rarely. This is usually because of some network glitches or the service being temporarily down, but SDK takes care of the tries in that case for you, and you usually don't even see that error. So it pretty much never happens, but partial failures happen all the time. And what you should do instead, looking at the error, you need to look at the response that you get from this. And the response contains the failed record count field. And if it's anything else than 0, it means that you had partial failure in your batch and you have to do manual redelivery yourself. And speaking about manual redelivery, you would want to use exponential backoff when doing redelivery, where each next retry attempt will be delayed exponentially. But it turns out that alone is not enough, because if part of your batch failed, it's probably because you have a stream that is overwhelmed, so you're exceeding the throughput of the stream. And then you start to send the retry attempts with exponential delay, like burst of retry attempts, and you end up overwhelming your stream even more. So what you should do instead is to try to spread your retry attempts as uniformly as you can. And for that, you can use a very simple technique called random jitter. So you just add random components to your delay, retry delay, and that way you distribute the retry attempts more uniformly and don't cause the stream to be even more overwhelmed than it was to start with. And this is a very, very simple technique, but it's very powerful. I personally saw a decrease of several thousand failed requests per day to a steady 0 after just adding this tiny little component. And once again, those things, they are related to all AWS services. It's not Kinesis specific. So if there's something I want you to take from this presentation, it will probably be the batch request and partial failure, and exponential backoff and jitter for retries, and also custom timeouts, because all of those appear again and again and again with all the services that you are probably gonna use in AWS. So very important stuff. So to wrap it up, some of the lessons we have learned. Well, always learn about service limits, because there are always limits, it's a fact. And there can be hard limits, there can be soft limits that you can increase, but the limits are always there and you better know about them before you start using the service. And one of the limits you need to keep a very close eye on, as I told you already, is the Lambda concurrency limit, because of its huge blast radius and the consequences it might have. On the same note, always dive deep in error handling. Each service has a different flavor of handling errors, so don't just assume things, as I used to do. Deep dive into error handling for each service you are using. And finally, to wrap it up with, once again, with words of Werner Vogels, everything fails all the time, especially when we are speaking big scale. So you better be prepared, and you better fail fast. Thank you.
All right, thank you, Anahit. And we got a question here in the Hoover app. Is there some kind of a back pressure mechanism at the individual steps? This came from Sven. I guess, Sven, do you mean the individual steps in the data pipeline itself?
Yeah, I meant you have some steps where the data comes in, you put this into what was it, Kinesis and Lambda and so on, and is there some general back pressure mechanism? But I think I asked too early, because I think your gotchas already answered it.
Right. Yeah, you're right. So there's no explicit back pressure mechanism per se, but the retries and error handling is acting as a back pressure mechanism in that sense. And on the other hand, Lambda can take care of a lot of retries on your behalf. So it's pretty much built in the way you handle your errors with these services.
Okay, and I did have some question as well. I was going to ask about the partial failures, but you covered that at the end.
That's my favorite topic.
Yeah, it's probably the first thing that came to mind every time I look at see something about the Kinesis. Also, did you hear that Kinesis launched the long-term storage today, or was it yesterday?
Did they already? I knew that it's coming, but I didn't hear that they have. So the material is already old.
Yeah, so, they announced it today, so it's now 1 year. I guess have you had any chance to play with that?
No, I haven't any chance to do anything with that. But we don't really in this particular case, we don't have the need to store the data for that long, or at least at the moment I can't see the use case for that. Probably we'll come up with something, but now we just use the basic default 24 hours retention, because everything extra costs. So 24 hours is fine for us for this particular case.
Okay, so I guess in that case, what would you do if something was to go wrong on the weekend and you haven't noticed until someone comes back in the office on Monday? Then you lose data, right? What would you do?
That's a good point. But as you know, it's very reliable, so nothing ever happens. Now, well, of course, we have the pager duty and stuff, so we are actually on call even on weekends and during the nighttime if something really bad happens. But I must say, in 3 years, or okay, we exclude the first year because we were a bit in a POC stage then, but now in 2 years at least, we haven't had a single issue with this pipeline, really, like zero. So I'm pretty confident in how it works.
Yeah, and I guess so. Also, I guess Kinesis is one of the probably the most scalable services within AWS. They use the AWS itself uses Kinesis for all the billing stuff. So everything that they charge you goes through Kinesis as well, right?
Yeah, and in addition to that, it uses Kinesis underneath as an underlying kind of service under the other services. So, for example, FireHost is built on top of Kinesis, and as far as I know, it's the biggest customer of Kinesis, actually, FireHost. And then things like IoT events and CloudWatch events, they are all built on top of Kinesis. So it's a very critical service inside AWS infrastructure itself. So in that sense, it's pretty reliable as well. And I think they are doing improvements on it all the time because they need it themselves. So.
And I guess in that case, I don't know if you have the numbers, but roughly, I mean, what sort of I guess the cost are you looking at for this kind of pipeline? Because one may ask questions around, okay, what if I just run something myself, like run a Splunk pipeline? What would the sort of cost comparison may look like in this case?
Yeah, I don't have any money numbers out of my head at the moment, but I would say that actually our Fargate cluster is costing, I think it's costing more than the Kinesis itself. So Kinesis is not a cheap service. It's more expensive than, for example, SQS, I think, if you do the comparison. But it's also not overly expensive. So we are speaking like pretty big scale in our case. And I would say something like, well, I don't want to lie, really. I don't want to say something, but like about 1,000 maybe a month or something like that, but maybe more.
Also, I guess I should just also quantify as well that I guess when you say it's more expensive than SQS, you're talking about per request.
Yeah, of course.
Kinesis has got a short hour, but I think when you are doing the sort of volume you are doing, it's going to be order of magnitude cheaper than SQS because the cost per million requests on SQS is quite expensive by comparison if you're doing a lot of traffic on actually making use of your streams. Because I did some work before on a project also, I think doing like something like a couple of thousand requests per second, and we look at the cost on SQS, and then we look at the cost for Kinesis, like if on say 3 shards, it was about $150 per month on Kinesis versus I think like a couple of $1,000s a month on the
Okay,
SQS.
that much.
Yeah,
Yeah, that's
because
it's a false belief in a way that well, of course, SQS. I think it's because SQS has a free tier, or like the amount of messages that you can send for free, and then kind of people get an impression that's very cheap. But again, on the bigger scale, things kind of change and they kind of rotate. And the fact that you have to pay for per shard per hour in Kinesis, it doesn't anymore make that much sense, because compared to the amount of data that so you're mainly paying for the data that you are streaming, actually, not for the open shards. And that's also why it's not that a big of a crime to have more shards open, because in the kind of grand scheme of things, that's not mainly what you're paying for. You're paying for that enormous amount of data that you are streaming through it.
Yeah, the shard hours that is significant only when you are doing a small amount of traffic at that point that you think, oh, that's quite expensive. I'm not really using it.
But it provides you with a lot of things that SQS can't. And actually, I've used it in several places instead of SQS with just one shard, in order to limit the Lambda concurrency to just one Lambda, because with SQS it scales kind of out of hand, and with Kinesis you have much more fine-grained control over the scaling.
Did you talk about scaling in that case then? Because I've had to build auto scaling for Kinesis myself a few times. Have you guys done that as well?
Well, it has been on my to-do list for a long time. I actually even started doing it, but then something got in the way. But the bottom line being, I'm optimistic, and I'm waiting for AWS to implement it on my behalf, because they have been promising that for quite some time now, that there's going to be auto scaling coming for Kinesis, and I'm a firm believer that it's going to come soon. I can neither confirm nor deny anything, but I'm pretty sure it's going to come at some point soon. So yeah, we decided to wait. Let's put it.
Okay, that's fair. I mean, they have got that one API call you can make, but you have to make it yourself.
Yeah, and you have to build the infrastructure around it. So you have to use something like 5-6 other components to kind of do the API, the auto scaling thing. And it's not complicated, but it's just kind of.
It's not complicated, but it's just you shouldn't be doing it yourself.
Exactly.